welcome to this session about the thermodynamics of ionic materials and the associated AFLOW module for this, which is the AFLOW-CCE module, where CCE stands for Coordination Corrected Enthalpies. And here we will learn how you can predict actually reliable and accurate formation enthalpies of ionic materials, and also cation coordination numbers and oxidation numbers, because this is what this correction scheme is based on. And I would like to outline that this work was funded by the Alexander von Humboldt Foundation through a scholarship. And to start out with, let's basically first talk about what ionic materials are. So when we look at the periodic table, what Dr. Osers was just mostly speaking about with this palladium, platinum, and manganese hulls were convex hull phase diagrams, including elements just 1 second, it's a little slow right now. It's just the elements marked in blue here. So these are the metallic elements of the periodic table, and when you intermix them and you form compounds there, you can plot these convex hull diagrams based on pure DFT data, because pure DFT is very accurate in this case, and you don't need to do anything else. So this is very easy to do and very straightforward in that sense. However, there's another part of the periodic table of these elements here marked in green, which are insulators in the elemental structure. And when you form a compound between the previously mentioned blue ones and these green ones, you get an ionic material, because you have the elements, the metallic elements with low electronegativity and elements with a high electronegativity, so that you form a polarization in your bonds, and that you essentially can also have strongly polar and ionic bonds in this case. So, and then you end up with these ionic materials in this case. And these ionic materials are, of course, very important in our everyday life. And I just want to highlight this a little bit on the next slide. So when you, for instance, think of oxides, which are the prototypical examples for these ionic materials, so they can be found in all kinds of applications, like transparent conductive oxides, or in battery materials, for instance. I have to apologize that the presentation is a little slow here right now in terms of loading. Let's see what I can get this a little quicker. So yeah, maybe let's start here again. So I can see when you think of ionic materials, you have, as I mentioned, these transparent conductive oxides, these battery materials, and even these ceramic coatings for airplanes and coatings for cutting tools. These are ionic materials. And of course, we want to be able to do materials design for this with AFLOW, but that's a fundamental problem from a scientific perspective. And this is what I would like to highlight here right now. So, and this is related to the formation enthalpy that Dr. Osers was already alluding to earlier. And I just wrote down the definition here again. So the formation enthalpy of a compound is defined as the enthalpy of that compound minus the stoichiometrically weighted sum of the enthalpies of those elemental references. And it turns out that when you calculate this for ionic materials, that this is a problem, that it is very inaccurate from pure density functional theory. And to underscore this point, I present here some real-world data for 71 ternary oxides. And I mean, it's a crowded plot, but the main message, I think, is rather easy to get. So I want you to focus on the data in this red box. And what is plotted here on the y-axis is the calculated formation enthalpy from DFT minus the experimental one. And so if all my points would be on the 0 line, I would be super happy, because then my results would be in perfect agreement with the experiment. However, this is not what we see. So if you, for instance, look at the green points calculated from PPE, you see that they are very far away from the 0 line, and that especially this is not a constant shift. There's a very large scatter involved here and very unsystematic. So the predictions that PBE gives you for the formation enthalpies of these oxides are very unreliable. And this is especially underscored by these mean absolute errors in this case, which are several 100 milli-eV per atom. And Dr. Osus was mentioning already before that the room temperature thermal energy scale is 25 milli-electron volts. And this means that with these predictions, you're so far off that you cannot do materials design at room temperature. So this is a problem, and you have to do something about it. And I just want to spend one slide to explain a little bit where this comes from. What is so fundamentally different compared to the other intermetallic compounds where DFT is so good? Yes, and the point is when we go back to this formation enthalpy, we have this difference property in this case. And when we look at an oxide, let's take magnesium oxide. So that the compound, the band structure of the compound looks something like this. So it is a ceramic insulator with a very large band gap. However, when you look at the elemental references, that would be pure magnesium, which is a metal. So your bands cross the Fermi energy here in blue, and a diatomic oxygen molecule, which is even spin polarized because triplet oxygen is the ground state. And this tells you that these structures and phases are all chemically very different. And you're trying to calculate a difference property between chemically different systems. And this is where DFT usually gives you a lot of errors, because there is what we, as we call it, a very bad error cancellation. And this can be underscored when you look at the density, the charge density that comes from certain states, which in case of these oxides or oxidic compounds is very localized for antications, whereas in the metallic states very delocalized. So you get a very different delocalization error if you're familiar with that. And so this means we have a very incomplete error cancellation and density functional theory here. And so this is the source why we get so bad predictions. But of course, we have to do something about it. We want to do materials design, and we want to also investigate convex Hall phase diagrams reliably for, let's say, oxidic systems. And so what can you do? And this is where this CCE, the coordination corrected enthalpies, comes into play. And I would like to motivate this from a structural perspective. So when you look, for instance, at calcium oxide, so this has a rock-solid structure where you have 6 calcium oxygen bonds in this fashion. So each calcium is coordinated by 6 oxygen anions. And then you can look, for instance, at the second structure, which is the rutile phase of titanium dioxide. In this case, you also have 6 titanium oxygen bonds. However, when you form the according ternary compound, which is perovskite, calcium titanium oxide, so kind of the prototypical ternary oxide, you find that you have 6 titanium oxygen bonds still, but 8 calcium oxygen bonds. That means your coordination number, the number of bonds, have changed. And in DFT, we are often discussing how well this theory captures a certain type of bonding. So when we assign errors, it makes therefore actually a lot of sense to assign them on a per bond basis and to correct them also on a per bond basis. And this is what you can do. So when you take, for instance, for binaries, this difference between the Cation and experimental ones, then you can assign these corrections per bond, and also specific to the cation oxidation state, which is also very important. And then you can apply them. I mean, I won't go through the details of these formulas, but I would just want to outline that once you have these corrections, then it's very easy to apply them and to calculate corrected formation enthalpies, in this case for ternary systems. And that's what we have done in one publication. So we have basically calculated for a lot of systems all these corrections and included them into this publication, into a very huge table. But you don't need to worry about this because all these corrections have been implemented into AFLOW. So this is just to give you an idea of what this is about and what in the background is actually happening. And now, of course, the question comes up: how good is this correction? And I show you this here again for the same set of 71 ternary oxides that we had before, where we had these hundreds of milli-eV per atom error. And when I correct the results with the CCE method, with the coordination corrected enthalpies, here on the scan functional, I get what is shown here in this graph. And now the y-axis is the difference of the corrected and the experimental formation enthalpies. And I had to even change the scale because the values got so much better, the agreement got so much better. Because the black symbols are now from my CCE method, from my corrected results, and I get a mean absolute error down to 27 millieV per atom, which is basically perfectly on par with room temperature thermal energy. And also it's noteworthy to say that this error is much smaller than the previous error of the method of quasi-fitted elemental phase reference energies. This is what FAIRES stands for, and it's almost twice as large. So our method is the only that is now really capable of going to this room temperature thermal energy limit in this case. So this is what CCE can do here. And I would like to show a second example because Dr. Osses was showing a lot of convex hull phase diagrams. And we have here a section of the convex hull phase diagram of the titanium oxygen system, where the so-called magnesium phases are plotted. So we go basically, we have here the formation enthalpy in the composition range from 0.6 to 0.7 in oxygen fraction. And you have these crosses are the experimentally known points. So for some systems, no experimental value or very reliable experimentally is known. And you see that plain PPE and also the other standard functionals like LDA and scan, they are very far off from these crosses. However, when you apply CCE on any of those three with the appropriate corrections, they're all on top of experiment and are within 10 to 20 millieV per atom of experiment. So this is really where this enables correcting the convex hull phase diagrams for these ionic systems, because if you only do DFT, you get the left one, and that's clearly not accurate enough. Yes, and then I would like to outline something that currently only the CCE scheme can do, because for some systems, you get a wrong ground state structure when you do DFT. So you find a certain crystal structure to be lower in energy than the experimental one that is known to be the ground state, so lowest in energy. And one example for this is actually this aluminum silicon oxygen system. There, a mineral called kyanite is known to be the experimental ground state. However, PBE, so the standard DFT functional, gives you a mineral with another name, with a different structure called andalusite to be lower in energy. And this is actually what is indicated in that graph. So you have the y-axis is the energy relative to the experimental ground state. This means my experimental ground state is at 0. And whenever I get a point below the 0 line, like this green point here for PBE, this is a wrong prediction, because you erroneously get something that is more stable than the experimental ground state. However, when I apply the CCE method and go from the green point to the blue point, this goes slightly above the 0 line. And this should also be the case because these structures are very close in energy. But importantly, it retains the correct energetic ordering in this case. And you can actually go further than this. You can consider more systems like calcium, like cobalt oxide and manganese oxide, so even transition metal oxides. There it works because they are known to have experimentally a rock solid ground state, but the standard functionals favor systems or structures with only 4 cation-anion bonds. However, when you correct them, so when you go to the black or blue points, you retain the correct energetic ordering. And this is something you can currently only do with the CCE scheme and no other correction method. And this is bringing this back to convex hull phase diagrams, very important, because plain DFT would give you a wrong convex hull here. It would give you the most stable structure as the wrong structure, and only the right structure would be above the convex hull. And only when you correct this, then you can actually get it right. Can get it also right the shape of the convex hull. And this brings me already after this scientific motivation or the scientific background, essentially, to the implementation of this coordination corrected enthalpies method. So this method has been fully automated in AFLOW. So what we will see is that you only need to provide a structure file, and the implementation will do everything else for you. And I start by outlining And you will also then see this on the command line. I will show this as an exemplary case on the command line. When you just use AFLOW --CCE, it's a very short command, then this will give you a dump to the screen, essentially README file or instructions how this method works, a little bit what is the background of the method, and what you can do with the method. What are your options? And we will go now essentially through this because the implementation features a command line tool, a web interface, and the Python environment. So we'll mostly focus on the command line tool, but you also look into the web interface and just mentioned the Python environment. So the workflow is sketched briefly here. As I mentioned, you first need to read the structure. So I see there's a question coming up in the chat. Why there is a big difference between CCE at scan and CCE at PBE for MNO slide 12? Shouldn't it be similar? Yeah, let's go back to that one. Yes. So you're basically referring to this, to this black point and this blue point. Yes, that's a good observation. That's a very good point. So that is something where we want to work on in the future. So I mean, getting qualitatively energetic ordering right, this is something that CCE captures very, very well. But the quantitative difference of this is harder to capture because these systems potentially suffer a lot from the self-interaction error. And what we think is that in order to get this quantitatively right, is that you need to include more structural information. So if you include this basic structural information like the coordination numbers, which you are currently doing, you get it qualitatively right, but for quantitative estimates or quantitative improvements, you basically need to go beyond that. And that's what we will do in the future. Yeah, very good question, very good observation. Thanks. So let me just go back here. And yeah, so what the workflow is doing is you read the structure file, and then first, since called coordination correct enthalpies, you have to determine the cation coordination numbers. And I showed this basically already before with this prototypical example of the perovskite system. The code analyzes your cation-anion bonds and gives you also back the cation coordination numbers. So even if you're not interested in the corrections, you can just get the cation coordination numbers. You'll see this and also do an exercise on that. I want to highlight that this implementation also finds what systems that are called multi-anion systems. So there is, for instance, this hafnium, tantalum, nitrogen oxide compound. And in this compound, both the nitrogen and oxygen are anions. And what this implementation does, it looks for every atom to which other atoms it is bonded to. And if it's only bonded to atoms of lower electronegativity than itself, then it must be an anion. And so in this way, I can easily find these multi-anion compounds, which are actually a direction of recent research interests. And I also want to highlight that it can treat peroxides and superoxides. So when you have peroxidic or superoxidic bonds in your system, it will also treat this correctly and find this correctly in this sense. So, and yeah, we will go through the slides first, and then I will show you these things also on the command line. So when you have a structure and you just type AFLOW -- get cation coord nums or coordination numbers, so there are a few overloads for this function, and then you pipe in your structure file, and what you will get back for this prototypical example is for all the cations in your system, which are calcium and titanium, atom number, and then this cation species and the anion for this cation species. So we see that all calciums in the structure are 8-fold coordinated by oxygen, and that the titanium atoms are 6-fold coordinated by oxygen, as I mentioned before. And so this you can already do without being focused on the corrections. So the coordination numbers might already be very useful by themselves. And then going one step further in the workflow, you have to next determine the oxidation numbers, because also the scheme is based on these cation oxidation numbers, which makes it very accurate, as we know. And this was actually a little bit harder to implement. And the algorithm to do this is sketched here. So I want to briefly go over this to give you an idea of how it finds the oxidation numbers in your system. So as I mentioned before, we know from the structural analysis what the anions are. And we assign to each of those anions the oxidation number, alpha, called here, and we take the lowest oxidation number that we know for this species. And then we have fixed the anions, and then we sort all the species ascending by electronegativity. I just want to briefly mention that we use Allen electronegativities since they seem to be the best ones, but it doesn't, yeah, this is basically just a detail here right now. And when you have sorted them, then we take the first cation species, which is the most electropositive one, and we assign to it the most positive oxidation number that we know. And then we go to the second cation species and basically do the same. The first oxidation number that we take is the most positive one. And we do this for a cation species and always assign this first most positive oxidation number. Then we have a first assignment of all the oxidation numbers, and then we check, is the sum of all the oxidation numbers 0? And if this is the case, then we regard this assignment as successful. If this is not the case, then we go back to this last level, to this most electronegative cation species, and change its oxidation state from the most positive to the second most positive, because you would expect that more electronegative species occur in lower oxidation states when they can, and the most electropositive ones occur in the highest oxidation states. And this basically can cascade through in this way, and it will thereby try all possibilities of oxidation numbers for the system, but direct it in a way due to the electronegativities. And I just want to briefly mention that we have checked this and we have tested this on a rather large set of ionic materials, on oxides, fluorides, nitrites, and the like. And it worked in basically every case. I mean, where we might have a few problems with the algorithm is in organic compounds, which is currently not the focus, because there you have these functional groups. And so other than that, we checked it on several hundreds of materials, and it always worked basically perfectly. And this is also, in that sense, can be useful by itself, because the algorithm provides this option AFLOW -- get oxidation numbers. And then you just type in your structure. And then it will give you back, again, in this tabular form, for each atom in the structure, the species of that atom and the oxidation state of that atom. And it can even, and we will see this in the exercises, treat certain tricky cases in this sense. And this is what we will see. There's a question in the chat. So it will recognize doped materials. Yes, I mean, it depends on, of course, on the level of doping, but yeah, when you have the doping correctly assigned in the structure file, then it will, yeah, then it will recognize this. Yeah. And then I think, yes, we already do the first exercises here on this functionality of the cation coordination numbers and on the oxidation numbers. I will just briefly read out the exercises. I guess maybe somebody else can try to assign the people to the breakout rooms that were unassigned before. And in the meantime, I will go through these exercises. So which
questions, Rico?
Sorry. Thank you, Marco. How efficient is this procedure for finding oxidation numbers in magnetic materials? I mean, there is no restriction to non-magnetic materials in this sense. I mean, for instance, we have tried it on iron 2+ and iron 3+ systems, and it finds the correct oxidation numbers. I mean, you can even have magnetite, which is a mixed valence system of iron 2+ and iron 3+, and it does that correctly. So I don't see any obstacle in that direction right away. For transition metal oxides or CCE tested with a DFT plus U level. Okay, that depends a little bit on what you mean. We have the corrections. We have also for our in-house DFT plus U calculations of the so-called ICSD database. So we can correct this database with the coordination corrected enthalpies method. If you're referring to the oxidation states, I mean, you might get from a DFT level when you do bother charge analysis. This is what I would think you're referring to. You might get more reliable oxidation numbers when you use DFT plus U instead of DFT. We did not need to resort to that because with the allen electronegativities, you get this basically for free. I mean, we have also implemented this for oxides on the bother charges, but the bother charge analysis is much less reliable than this. Just let me see. Is it possible to use CCE to correct analysis in your data? Yes, and we will see this in the second part. So you only need your structure file and maybe pre-calculated formation enthalpies and for your structure, and then it will correct it directly for you. I mean, we have it parameterized so fully for oxides and nitrites, and we'll right now go ahead for all other ionic materials. So that is not restricted to the database. Yeah. Is there a restriction on the number of atoms? No. As long, as you can read it, and I mean, we will see one example where we have almost 100 atoms in the unit cell, and this is without any problem. So there's no restriction on the number of atoms. Yes. Okay. Then let me just get back to the exercises. So the first question is, which cation coordination numbers does CCE provide for this natrium tungsten nitride, for yttrium oxygen fluoride, for ammonium nitrite, and for this rather complex compound, silver chlorine fluorine molybdenum oxide. And when you do this analysis and you look carefully, then you can find out which of these systems are multi-anion compounds. And I will show you basically how to do this, first with an example, and then with the directory structure that you have in the VM. And then the second question is, which oxidation numbers does the CCE algorithm provide for lead molybdenum oxide and for casterite, like this copper, zinc, tin sulfide? Because these are tricky cases. And I also ask you, what would you expect? So which oxidation numbers would you intuitively assign? Because there is a disambiguity in both cases. And there you can also use the postcards. And I just want to briefly move over to the VM. So we have here on the VM the directory structure, and when you just go to the AFLOW exercises directory, then we have the day 3.1 today in this case, and then we descend further down to the 0.5, the CCE. And when we do this, there's already the README of the AFLOW-CCE module, which basically includes the information that I outlined before. And then there's a sketch in the exercises directory. And we go first, before we do the exercises, into the sketch directory. And what I just want you to show is when you type AFLOW -CCE, then you get these explanations dumped to the screen. Who wrote the code and what are the publications that are related, and some basic instructions and the options that you have. And you get an example structure file in this case. And you can basically mark that and copy that one. And then you can, let's call it postcard MGO. And I do this with VI, so you can do it with Gedit, as previously shown. I just do it with VI because I'm more familiar with that. And then you can essentially just paste this structure. It will ask you again, should I really paste it? And yes, you should insist here. You should really do it. And then you save it in this case. And then I can show you the basic commands that you need for the exercises for in this example. So when you do AFLOW -get cation coordinates, and then you pipe in this structure. This is, of course, not a very long output because the oxide structure only has 2 atoms in the unit cell. This will be different in the examples, but you see that you have 1 magnesium, which is coordinated by oxygen and 6-fold. So in octahedral geometry. So this is this command. And then we can basically also show the second one in this example case. Then there are a few overloads. So you can even just write get oxnums, or let's write it out here. In this case, get oxidation numbers, and you pipe in again the Posca of this magnesium oxide system. And then you get, as you would expect, that magnesium is +2 and oxygen is -2. And this should equip you with the tools that are needed in the exercises. And with that, I go back here to exercises, and then I think we should go to the breakout rooms and maybe spend 10 minutes, or let's say 8 minutes until 16:40 Central European summertime, which should be about 8:40 in the Eastern Daylight Time. Okay, then let's go to the breakout rooms, and if there are no further questions, and I will stop sharing for the moment. So yeah, welcome back. Let's wait for the others to move out of the breakout rooms. Most of them look pretty empty. In the meantime, I think I already start sharing the screen again. Yeah, so I guess most of the people, or pretty much all, should be back. So let's then go to this directory number 2, exercises. And yeah, so there's this first subdirectory with the coordination numbers exercise. And there we can basically perform this analysis. So if we hit up the command line, we can go back to this command to get the cation coordination numbers, and we can just substitute this in this case with this sodium tungsten nitrite nitrogen compound. And when we do this, I selected here a nitrite to have something other than oxides in this case. And here you can see that we have 2 cations in the system. This is sodium and tungsten. They are coordinated by nitrogen, in every case 4-fold. But this is a single anion system, if you wish like that. And the second example would be this yttrium oxyfluoride, a small structure, but interesting in the sense that here you have listed this yttrium atom number 5 2 times. So it is 4-fold coordinated by fluorine, and another 4 times coordinated by oxygen. So the whole coordination number would be 8, but it's a multi-anion system. So half of it is fluorine and half of it is oxygen. So this is the first multi-anion system. Then the ammonium nitrite. This is already, as I mentioned, a relatively large structure, so there's really no restriction in the number of atoms that it can treat. And this is interesting in the sense that you have complex ions. We have the ammonium ion and we have the nitrite ion. And for the ammonium ion, this NH4+, of course, the hydrogen is the cation, and it is coordinated 1-fold by nitrogen. So all these hydrogens are 1 time coordinated by nitrogen in this case. as indicated here in these lines, up to atom number 32. And then there is another sort of nitrogens, the nitrite nitrogens, which are now cations in this case, and they are coordinated by oxygen threefold in each case. And this is the other anion, and this shows this is a multi-anion compound because nitrogen and oxygen are the anions. At the same time, it is a mixed valence compound because nitrogen occurs once in oxidation state -3 and oxidation state +5. So this is a very special compound, and an interesting case in that sense. Just looking into the chat, are there any questions? Okay. Then the last example is this complex one, the silver, chlorine, fluorine. I just selected that one to show the diversity of what you can get. So you actually see here that you have 3 anion species in the system: fluorine, chlorine, oxygen. And this first silver atom is coordinated by 2 fluorine, 1 chlorine, and 3 oxygen atoms. The same is true for the second silver and the third silver. However, the fourth silver atom is coordinated by only 1 chlorine and 4 oxygens. And this is also mirrored by the 5th and 6th silver cation. And then the molybdenums are also interesting. So one molybdenum is only coordinated by 4 oxygens. On the other hand, the other molybdenum atom, atom number 12, is coordinated by 3 fluorine and by 3 oxygen atoms. So this is a very complex multi-anion compound with 3 different anion species and very different also cation coordination environments. And this is what you can easily analyze essentially with the CCE module. Yes. So with that, we go to the subdirector number 2, the oxidation numbers. And there are 2 postcard files in this directory, and we can go up to determine them here. Let's do first the one that is also mentioned as the first one in the exercise, the lead molybdenum oxide system. And there you see molybdenum is in oxidation state +6, and lead is in oxidation state +2. And on the slides, I will actually show a little bit the disambiguity that you might have here. But this is really based on electronegativities, that the molybdenum is the more electropositive one, and so it should be in the higher oxidation state instead of the lead, because they could also be both +4. So I will also show this in a periodic table on the slides in a second. So this is what this gets here. And then we can do the same for casterite. So we just hit up and substitute our postcard with the casterite postcard. And what we see there is that the copper, so you have 2 copper atoms, 2 copper cations, they are both +1. Then you have the sulfur, which are all -2. Then you have 1 tin, which is +4, and the zinc, which is +2. And this is interesting because copper could also be +2 and tin could be +2. That would also make the sum of oxidation number 0. However, that would not respect the order of the electronegativities because copper is less electropositive in this sense than tin. So this is what is basically indicated here. And I have this briefly also highlighted on the slides in this case. Because when you look to the molybdenum lead one, so lead can be +2 or +4. It can give away only the P or also the S electrons. And molybdenum can be +4, giving away the D, or also give away the S, could be +6. But the correct one, the correct ordering you get when you look at the ion electronegativities as the implementation does, and then you get molybdenum in +6 and lead in +2 oxidation state. And similarly, as I mentioned before, with the casterite example, that the tin needs to be +4 and the copper is +1. Okay, so I guess this gives you an idea of what you can do or what the CCE tool can do in terms of cation coordination numbers and oxidation numbers. And now we go to the final part of our workflow. Essentially, we can include also temperature effects right away in the corrections. So you only provide a structure, you haven't done any temperature calculation, but you can include those temperature effects in the corrections. And the way this works is briefly sketched here. So at room temperature, what you take for the fitting are experimental room temperature formation enthalpies. And when you fit your DFT corrections to these values, what you get is room temperature corrections, meaning that when you apply them, you get a direct estimate of the room temperature formation enthalpy of your compound. And on the other hand, when you are interested in the 0 Kelvin formation enthalpies, you can play a little trick in the sense that you start again from the experimental room temperature values, but you subtract from that the calculated thermal contribution to the formation enthalpy, which we can do for our fit set. And then you get an estimate for the 0 Kelvin formation enthalpies. And when you fit to these, your corrections, you get 0 Kelvin corrections, meaning that when you apply those, you get a direct estimate of the 0 Kelvin formation enthalpy. And we will also see this in the example. So this is also a special feature of this correction scheme. The temperature effects are included in the corrections without additional computation. Yes, and this is then basically the end of the workflow, where it can then return the corrections and corrected formation enthalpies. And then we will then just go through how this looks like. I have actually another slide right away, where you can see how the output of the actual correction scheme. So when you type AFLOW -- get CCE corrections and you type in your structure file, so then you will get back for each of those 3 functionals and for 2 temperatures the corrections in this format. And I just want to structure it a little bit in the sense you first get the corrections in this box highlighted here. So for PBE, you get for room temperature the correction per cell and the correction per atom. And then also for 0 Kelvin, the correction per cell and the correction per atom. And in the same way then for LDA for both temperatures and for SCAN for both temperatures. And then in case you specify no pre-calculated formation enthalpies, there is also a little highlight of the code that gives you some sort of rough guess of the formation enthalpy of the compound, which is based on experimental formation enthalpies. So without doing any DFT calculations, you just pipe in the structure, then you get a rough guess of the formation enthalpy of the system at low pressure, I should say. But this is a detail. And the accuracy of this is actually as good as a plain DFT calculation for these systems. So this is what you can do here in this case. And then there's another command. You can type AFLOW -- CCE equals the structure, the path to your structure file. And when you do this, you get the full CCE analysis, meaning, as I have highlighted here, you get the cation coordination numbers, you get the automatically determined oxidation numbers, and you get the CCE corrections, as well as this rough guess for the formation enthalpy. And I did this here, not for the perovskite example, but for the magnesium oxide, because for perovskite would be too much of an output to fit on the slide. But if with this, you can get all the analysis in one stroke, essentially. And then there are a few options that you can also add to the code. So if you're, for instance, interested in getting only the corrections for specific functionals, you might only be interested in PBE, let's say, then you pipe in your structure that way, and then you just have the option -- functionals equals PBE, and then you only get the PBE correction. And then you can provide, and this was also mentioned before in the chat, essentially, when you have your own data and you have calculated formation enthalpies for your own data, then you can provide these pre-calculated values as enthalpies formation DFT with these as these comma-separated list. And then, of course, you need to provide to which functionals they correspond to. So the sequence of these numbers must be the same sequence as the sequence of functionals here on the back. And then it will give you automatically the corrected values of the formation enthalpy. So you will see this in one of the exercises. And in case you're not happy, I mean, I don't have a case for that, but you're not happy with the arithmetically determined oxidation numbers, there's in principle also the option to provide the oxidation numbers as a comma separate list for all atoms in the structure as an additional option. And the final option would also be that you obtain the output either in table format or as a JSON file. So you can, similar to the other modules we have seen, you can simply type -- print equals JSON, and then you get the JSON command. You get the JSON output. Yes, and then there's also what I would like to highlight. There's the web interface of the implementation. And for this, I might just quickly go back to the virtual machine, because we can also look this up here. So when you go to your browser and you type something like aflow.org, then you go to the AFLOW page, and then when you select the panel, the AFLOW Online, which we have done with Dr. Hicks already for the symmetry analysis, then there's also a CCE functional. When you scroll down on this page, and you let it stop here, yeah, then there is a section called coordination corrected enthalpies, which includes all the functionality that you also have on the command line. And you can, for instance, activate CCE, and then it gives you this magnesium oxide example, and then you can hit submit, and then you will get the output of this of the whole CCE analysis in this case, so the cation coordination numbers, oxidation numbers, and the corrections in this case. There's this, and you can also with this determine the oxidation number. So there are additional buttons for determining the oxidation numbers, which again for the magnesium oxide example are +2 and -2 in this case. Yeah, this is what I wanted to highlight here, that you have also all the functionality essentially on the web end. And then I'll just briefly go back to the slides. So the web tool was developed together with Max Brenner and Stuart Key. And then I think we don't have time to go through the Python environment here. So I just briefly mention that the implementation also includes a Python module in the AFLOW source directory, which you can load into your Python script, and then you can provide the pre-calculated formation enthalpies, the functionals, and you will get a Python dictionary back that you can then use in your research for this. Yeah, so there's the question, but the CCE data are not in the property filters. Not yet. This is something that we are working on. So the CCE is a rather new development in the database, and this is exactly something we are looking into of including. At some point I mentioned this only for oxides and nitrites. Is that correct? So the point is the full CCE correction is parameterized currently for oxides and nitrites. However, the cation coordination analysis and the oxidation numbers, this works for everything, or for all ionic materials, or for all materials essentially. But for the full corrections, I mean, we have the oxides and nitrites right now, and we will continue with the other anion compounds. But the code will tell you this essentially, that if it doesn't know a correction for a certain system, it will tell you that. And this is this is something that we will carry on the parameterization in the future. Yes, and yeah, I want to just briefly mention those Python functionality, which I won't go into detail right now. I want to rather focus on the other exercises for the corrections in this case. So for the first exercise here, you should use the search page to retrieve the relaxed structure of the magnesium tungsten oxide system with space group 13 and person symbol MP12. And I mean, you can do as you like. You can insert it into the CCE web tool or use it on the command line and determine which function has the largest CCE correction for magnesium tungsten oxide at room temperature. And in the second example, you should use the search functionality of the Prototypes web app to find perovskite, what Dr. Hicks showed yesterday, with stress group 62 and person symbol OP20, and then generate the WASP output. And then you can use this WASP output in the command line together with these pre-calculated formation DFT formation enthalpies to calculate corrected formation enthalpies based on the options that I outlined before. I will just exit this mode, and for this first question, I think that has only been mentioned once. I just want to highlight how you can retrieve the relaxed structure of a certain system. So the magnesium tungsten oxide, I will let you search alone. But if you go to the search page and you look, for instance, for magnesium oxide, and you say, I want to have 2 species, and you hit enter. Then you have then you can go to any of the entry pages of the magnesium oxide. So this is just to show you again where you get the relaxed structure. And if you then are at this entry page and you scroll down, in this case, the virtual machine is a little bit slow. Yeah, you will scroll down. Then you can finally find this section relaxed structure, and then get the WASP postcard on that. So that was maybe a little bit quick, but you have down here by downloadable files this relaxed structure, and then when you just hit WASP concar, then it will give you the concar WASP, which you can then copy and insert either into the web tool or onto the command line to solve these exercises. So that is just what I wanted to outline very briefly. And then I just go back here, make the browser a bit smaller, and then just show you. I didn't show this before, so that was a little bit maybe quick. But when you're in this exercises directory right now, so the directories where you should work in is now this 3, the CCE corrections, and the 4, the CCE formation enthalpies. I mean, you get the structure from other web functionality, but you can actually solve it in there to keep the order of your structures. So, and with that, I would say let's go into the breakout rooms. I think we are a little bit beyond time. Let's go there for 9 minutes, and then then we will come back and then quickly wrap up before we can continue. Okay. If there are no further questions in this case. Then just wait a minute, and then we can, until it's 5:10 p.m. Central European summertime and 11:10 at the East Coast in the US. Okay, then let's head to the breakout rooms. A few more seconds. Yes, I will start sharing my screen again. Okay, so then let's maybe wrap up that exercise. So the first task was to use the search page to retrieve this magnesium tungsten oxide system, space group 13, person symbol MP12. When we do this, at the AFLOW.org search page. So you have your magnesium tungsten oxygen. Restrict the search to 3, and then search for that. Then you get a bunch of entries with all the same structural data, with the same space group and person symbol, so it doesn't really matter which one we take. So let's take the first one. And then we can essentially scroll down the page. And there we are at the very bottom to get the VASP concar. Then we can copy that. And if you go back to the main page to go to the AFLOW online app, to the CCE web tool, since I wrote to maybe do it with the CCE web tool, then you first activate CCE. And then you have to get rid of the magnesium oxide structure. And then you just paste the structure you just have found via the search page. So these exercises are also a little bit to interconnect the different functionalities that we have shown, that you can get a structure from a certain application in AFLOW and then use it in another application. And when you submit that, then you get the results of the full CCE analysis. I believe this is maybe a little bit small. So if I zoom in a little bit more, you can actually also read that. And then we see that in this table, which gives us the corrections, somehow LDA is the winner in this case. And I asked explicitly for room temperature. So it would be for room temperature minus 2.464 per cell, or minus 205, let's say, millieV per atom. When you do a normalized per atom basis. So it is that part of the exercise. And then you have the other exercise with the number 4, to use the search functionality of the prototypes web app for the perovskite structure and to generate the VASP output. So when we go for that, so we go to these prototypes app in the browser, and then you use either of the search bars to look for perovskite. And then you have different perovskites. The one I indicate with the space group is the first one. This is the 62 one. So when we take that one, then you go to the entry page. The structure takes a little time to load, and then you just scroll all the way down so that you can generate the VASP output. And then we essentially get this output here. It's a little hard to navigate inside the VM. We do this, and we can copy it, and then can move that down. And then I just go for clarity into this directory for CCE formation enthalpies. And I open, in my case, FBI. You can also do the same. Get it, a Pascal perovskite. And then you can basically paste the structure in there. They asked us, do you want to do this? Yes, we want to do this. And then we write the file and close it. And then we have this perovskite structure, and then we can say AFLOW minus CCE, let's say, for the full analysis. Or let's take the get CCE corrections, and we pipe in this postcard, and then you have to use the other functionalities, minus enthalpies formation DFT, which are in this case, let me see if I can bring this up somehow in parallel on the screen. This is a little bit difficult, but we can see that we have here essentially minus 63.452, minus 72.084, and minus 72.412. So it is always assumed that stable compounds have negative formation enthalpies. And then we need to give it the functionalist tag in the same sequence. as the formation enthalpies. And this would be, as a comma separate list again, PBE, LDA, and scan. I will answer to the chat in just a minute, because we can then just hit enter, and then we get this output with the corrections, and now also finally corrected formation enthalpies. And I asked for the corrected formation enthalpies at 0 Kelvin for PBE. Let's do it on a per atom basis. It's minus 3.449. For LDA, it's minus 3.412, and for scan, it's minus 3.414. And you see that what also should be the case, they are very, very close. So it doesn't really matter which functional you correct, as long as you do it with the as you do it consistently, you get very good values that agree very well with one another.